Okay, so in the last class we discussed the limit of your function of two variable at a point. Okay, and then we discuss about the continuity. And the last class we discussed one problem. Okay, we have to simplify that problem. So quickly we recall. Okay, we solve that problem. So what is the problem? I think limit x comma y goes to 1 comma 1, but x not equal to 1. F of x is xy minus y minus 2x plus 2 by x minus 1. Okay. So if you directly substitute x equal to 1, y equal to 1, you will get the denominator is 0. So simply you can simplify in the numerator. You can take y outside from the first two term, you get x minus 1. From the second last two term, you can take minus 2 outside, we get x minus 1 whole divided by x minus 1. So now you take limit x comma y approaches to 1 comma 1. Now we can simplify again this, we can cancel this x minus 1, we get y minus 2. Okay, so if we apply limit x comma y approaches to 1 comma 1 is nothing but there is no x term, therefore directly you can substitute y equal to 1, we get minus 1. So minus 1 is the limit of this function. Okay, now we discuss about the derivative of a function at a point. So here, but in the function of one variable, we have only one independent variable. Therefore, we can talk about the dy by dx. So derivative function at one independent variable. Okay, in the function of one variable, we discuss about df by dx, because f is a function of x alone. That is otherwise we call y. And we know that at a point x equal to a, or we simply write f dash of a in the function of one variable is we define like limit h goes to 0, f of a plus h minus f of a by h. If the limit is exist, then we say f is differentiable at a point a. So suppose here f is a function of two variable. Now we can discuss about, but here there are two independent variable x and y. Therefore, what is the derivative of f with respect to x, and what is the derivative of x with respect to y? So we define as a partial derivatives. Okay, so more than one independent variable, the derivatives we called partial derivatives. So definition, the partial derivative of f with respect to x. So the partial derivative of f of x comma y with respect to x. With respect to x at a point, at the point some x naught comma y naught. What is the derivative of a function at a point x naught comma y naught with respect to ax is the limit exists. What the limit? So usually we denote f suffix x, that is derivative of f, otherwise partial derivative we write dou f by dou x at x, we are at the point. So we write dou f by dou x, derivative of f, partial derivative of f with respect to x. After that you have to substitute the point x naught comma y naught. So here we have to treat y as a constant. Therefore, this is nothing but you have to directly substitute the value y equal to y naught, and then usual differentiation with respect to x, d by dx of f of x comma y naught. But here we start with the f of x comma y. So here we have to treat y as a constant. Therefore, you have to substitute y equal to y naught. Now we get a function of one variable, namely x. Now it's nothing but ordinary derivative. Now, when this limit exists, limit, just we can say f of x plus h comma y naught, because only the first variables vary, second variable is fixed, minus f of x naught comma y naught by h. If the limit h goes to 0, if the limit exists, then we can write this is a derivative of f with respect to x at a point x naught comma y naught. So simply we can say f suffix x at a point x naught comma y naught. Okay, so this is a partial derivative of f with respect to x. Similarly, we define the partial derivative of f with respect to y. So next definition. So the partial derivative of f with respect to y. If partial derivative of f of x comma y with respect to y. With respect to the another independent variable y at the point x naught comma y naught is again dou f by dou y at the point x naught comma y naught is nothing but here we have to treat x is a constant. Therefore, ordinary derivative with respect to y f of x naught comma y. So this is nothing but limit h goes to 0 f of x naught comma y plus h minus f of x naught comma y naught divided by h. If the limit exists, then we say the derivative, partial derivative of f with respect to y exists. Then we denote f suffix y at a point x naught comma y naught. If both the partial derivatives exist, then we say the function is differentiable at a point x naught comma y naught. Okay. Now we discuss some problem to find the partial derivatives. So provided we say, so maybe you can say the definition. If we say that f of x comma y is differentiable, at the point x naught comma y naught if both the partial derivatives, that is f suffix, that is partial derivative of f with respect to exist at a point x naught comma y naught, and partial derivative of f with respect to y at a point x naught y naught exist. Just exist, need not be equal. So if both partial derivatives exist, then we say f is differentiable. If one partial derivative exists but another partial does not exist, then we say its function is not differentiable. Again, a function is differentiable on the set if it is differentiable to every point on the set. Okay, similar thing. So example, exercise. Suppose find the values of okay, suppose we have a function of two variable f of x comma y is x square plus 3xy plus y minus 1. Okay. So at a point 4 comma minus 5, check whether the function is differentiable or not, or find, okay, check the function is differentiable or not. Is f is differentiable at a point. At 4 comma 5 or not. So you have to find the fx fy. So actually it's nothing but we can directly find the value. We have to treat y as a constant and then difference. So derivative of 2x square is 2x and derivative of 3xy, since 3y is a constant, derivative of x is 1, the derivative of y is 0, derivative of 1 is minus 1 is 0. So this is fx. Now what is the value at a point 4 comma minus 5? So substitute x equal to 4, therefore 8 minus 15. So therefore 8 minus 15 is minus 7. So fx exists. Now what is fy? We have to differentiate with respect to y. Treat x as a constant, therefore x square is 0, and therefore we get 3x plus 1. And then derivative of 1 is 0. Now what is the value at a point 4 comma minus 5? So if substitute x equal to 4, we get 12 plus 1. There is no y, therefore it's 13. So therefore both the partial derivatives exist, therefore f is differentiable at a point. at the point 4 comma minus 5. Okay. Now, next exercise. So exercise 2, suppose f of x comma y is y into sine xy. Sine of xy. So what is fx? So find dou f by dou y. That is what is fy. So you have to treat x is a constant, but this is also function of x. This is also function of x. So since x is a constant, therefore you have to apply this ordinary derivative with respect to y. Therefore you have to apply this is u into v. So fix y and then differentiate sine xy. Derivative of sine xy is cos xy. But what is the derivative of xy? Just x, because x is a constant. Derivative of y is 1. So plus fix sine xy and then differentiate to y with respect to y, we get 1. Therefore, this is nothing but xy cos xy plus sine of xy. So this is a partial derivative of f with respect to y. Okay. Any doubt in this? Maybe I will ask one more question. If you divide some other function, maybe. Okay, I can write some other example. Suppose the function f of x comma y defined by xy into x square minus y square by x square plus y square if both xy is non-zero. Okay, and 0 if xy is 0. Now find the derivative of f at any point. So anyway, first you got to check the derivative of 0 0 at a point 0 0. Okay. So what is fx? So the definition fx of any point. Suppose if you want to take 0 0, suppose I'm taking 0 0. So this is nothing but limit h goes to 0. Since we are differentiating with respect to x, the second coordinates is constant. Therefore, f of 0 plus h comma 0 minus f of 0 comma 0 by h. What is the limit of this? So this is nothing but limit h goes to 0. So 0 plus h is nothing but h is nothing but f of h comma 0 minus f of 0 is 0 because the function defined at a point 0 0 is 0 by h. Now, since h is non-zero number, okay, so therefore, what is f of h comma 0? You have to take this first one. So this is equal to the product. Anyway, here y is 0. So therefore, automatically 0. So 0 minus 0 by h. And then you can take the limit. Because y is 0, but here y is in the multiplication, the function. Therefore, 0 into anything 0. Therefore, we get the derivative of a function with respect to x at a point 0 comma 0 is 0. Okay. Now, similarly, you can find derivative of y at a point 0 comma 0. So here x is a constant. Therefore, limit f of 0 comma 0 plus h minus f of 0 comma 0 by h. So therefore, limit h goes to 0. So this is f of 0 comma h minus f of 0 is 0 by h. Again here x equal to 0, y is h, but again x is a multiplication. So x into y, therefore automatically 0, 0 minus 0 is 0. So even if you take the limit, we get 0. So therefore, f is differentiable at a point 0 comma 0. Okay. Now, suppose if you want to find derivative of some other point, okay, suppose if you want to take want to find the derivative of at a point 0 comma some k, okay, again similarly you can check what is the derivative of k comma 0. So all possible thing. Okay, so first maybe first we fix some x is non-zero, y is 0. So at the point we have to check the function is differentiable or not. So at some k comma 0 at a point, what is the derivative of your function with respect to x at a point k comma 0? So this is nothing but limit h goes to 0 f of x plus, okay, sorry, not x, here k plus h, because here y is fixed, that is constant. So k plus h comma 0 minus f of k comma 0, because we are going to find that at a point 0 k comma 0 whole divided by h. What is the limit of this? So again, since if at least one coordinate 0, the product is always 0, because the function is always 0. Because in the function, if at least one of the x is 0, the function is like xy into x square minus y square by x square plus y square. So the product is xy. Even if one of the coordinate is 0, then automatically the function is 0. So therefore, here, therefore f, the first one is 0, this is 0, and this also 0. Therefore, total is 0. So therefore, at the point k comma 0, the first derivative is 0. Suppose if you find, similarly, if you find the first derivative of y at the point same 0 comma k comma 0, what is the value? Limit h goes to 0. Here x is constant. Okay. So what you'll get? K comma 0 plus h minus f of k comma 0 by h. Okay, because the point is k comma 0. So but x is constant, but y is varying, therefore we got to add h to the second coordinate. Okay, therefore 0 plus h. Now already we know that k is non-zero, h is non-zero, therefore this is equal to limit h goes to 0 f of k comma h minus f of k comma 0 is always 0, because if one coordinate is 0, the function is 0 by h. Now what is f of kh? K is non-zero, h is non-zero, therefore the function is nothing but limit h goes to 0 xy, the product k into h into x square minus k square, therefore k square minus h square by that one, what is that, plus k square plus h square by h, therefore it's nothing but h. So you can cancel this h. Now if k h approaches 0, what you will get? In the numerator we have k cube, because h square is 0. The denominator we have a k square, because h is 0. Therefore we get k. We get anyway k is some constant, is fixed number. Okay, if we take k equal to 2 comma 0, then the derivative is 2. Okay, so the derivative of y exists at a point k comma 0 for any k non-zero. Similarly, we can apply find the derivative of 0 comma k. Okay, so this is a method to find the derivative of a function with respect to any one of the independent variable at a point. Okay, maybe I ask one more question. So similarly, if once you define the first derivative, we can ask the second derivative, higher derivative. What is the derivative of the function, now new function, once fx is differentiable? Then we can differentiate the function with respect to x. So simply we can write this is nothing but fxx. So second derivative. So this is nothing but actually limit h goes to 0. Instead of f, we are using the function fx. Fx of here x is varying, therefore yes, x plus h comma y is constant minus fx of we are talking about the point x comma y. by h. We are talking about this limit. Suppose you have to differentiate the function fx with respect to y. This is nothing but we denote fxy. So this is nothing but here we fix x is constant. Therefore, what is the limit? This is nothing but limit h goes to 0. Fx of, because function is fx, but we are going to differentiate with respect to y. Therefore, x is constant, but y is varying. By h. If the limit exists, that is fxy. So similarly, we find fyy. So we know fy. Again, if you differentiate the function with respect to y, this is nothing but fyy. So again, this is nothing but limit h goes to 0. Fy of fy is a function. Here y is varying, x is fixed. By h. So again, we can differentiate fy with respect to x also. Fy with respect to x is equal to fyx equal to limit h goes to 0. Fy of, here x is varying, therefore x plus h comma y minus fy of x comma y at a point x comma y whole divided by h. In general, this f of x comma y, f of y comma x need not be equal. So in general, this derivative of xy is not equal to the derivative of yx. Okay, it's very important thing. So when these two are equal, so that is called there are so many theorems, Young's theorem or Euler's theorem. So if each of these are even fx, fy, everything is differentiable and continuous, then it is equal. So maybe you can state the theorem. So when these are equal, so theorem. So the theorem says, suppose f of x comma be a real valued function such that the second order derivative partial derivatives, suppose if both are continuous at a point x naught comma y naught, a comma b. Suppose if, so you write all the stories, simply I'm writing. So this fxy, this is one function, and fyx, both are continuous, or continuous function, continuous at a point some a comma b, then both are equal at a point a comma b. That is fx comma x fxy of ab equal to fyx ab. So this is one theorem. So both the second partial derivatives are continuous at a point a comma b. Then at the point a comma b, both the functions fxy, fyx are equal. So therefore, this fxy, fyx continues at every point, then the two functions are equal. Okay. So, there is another theorem. That theorem is called the Schwarz theorem. So theorem. So this is called Schwarz theorem. So this theorem says, again, when these two functions are equal. Okay. So assume that again f of x comma y is a real valued function of two variable all the things. Okay. So suppose the first condition is the derivative of y, derivative of f with respect to y exists on certain neighborhood of the point a comma b. Okay, suppose a comma b is here, the point. So neighborhood is nothing but just some open set. Okay, so we can draw so many neighborhood. So this is one of the neighborhood, or if you take this is a one neighborhood, or neighborhood is nothing but it's a open set containing that point a comma b. That is a neighborhood. So if you take any point, there are so many. We can draw so many neighborhood. For example, if you take the point, if you take 0, 0, so the neighborhood of 0, 0 is nothing but you can take circle. Circle is a neighborhood because you can find a open set inside this one. So we can draw so many circles. So there are infinitely many neighborhoods. But the function need not be differentiable to every point of the neighborhood. But the theorem says, suppose the derivative of f with respect to y exists on certain neighborhood of a comma b, but not all the neighborhood of a comma b. That is the first condition. Okay. Okay. Now the second condition is the fxy. The second partial derivative fxy is continuous. Is continuous at a point a comma b, then this fyx always exists. Then the partial derivatives yx exist on at a point. Okay, exists at the point a comma b, and both are equal. And this fxy second derivative at a point a comma b equal to fyx of a comma b equal. Both are equal. Okay, provided the fy exists at certain neighborhood of a comma b and fxy is continuous at a comma b, then the fyx exists. So this is Schwarz theorem. So another theorem is called Young's theorem. So again, Young's theorem says when these two functions are equal. Theorem. So this theorem is called Young's theorem. So also there is another theorem is there that is called Euler's theorem. But okay, anyway, what is Young's theorem says, again, f of x comma y is a real valued function of two variable is defined on some neighborhood of a point a comma b. Okay, suppose okay, I can write the first condition is, so the first order partial derivatives fx and fy are differentiable at a point. So both are differentiable at the point a comma b. So again, that is the new function fx fy is differentiable at a point a comma b. This is the first condition. If the suppose the first derivative is fx and fy are differentiable at a point a comma b, then this fxy at a point a comma b equal to fyx of a comma b. Both are equal. Okay, so this is a Young's theorem. So okay, so another theorem, that is Euler's theorem, says suppose if fx, fy, fxy, fyx are all continuous, then both are equal. Okay, so that is sometimes called as Euler's theorem. So if the function f, fx, fy, fyxy, these are all function yx are continuous, all are continuous, then at a point a comma b, then this fx of a comma b, simply say fx equal to fyx. This is Euler's theorem. Okay, any doubt in this? So okay, maybe we discuss some example. It is asked in the JAM exam. Partial derivatives of a function. Okay, 1 minute, I will find the problem. Okay, anyway, we will solve the problem. If I found, I will write, otherwise. Okay, now we move to the next thing. If I found the problem, I will discuss. Okay, so for we say yeah, when function of two variables is differentiable, when we say a function of two variables is continuous. Okay, we can extend this into three variables. Suppose function of three variables nothing but is defined. Now we take some subset from R3. Okay, so if we take D is a subset of R3. D is some subset of R3. Then any function from D to R is a function of three variable, because there are three inputs x, y, z, and then it gives some value, some t or something. So this f is called function of three variable. Again, now what is the limit at a point? Same thing. We have to suppose what is the derivative of. So here there are partial derivatives fx, fy, fez. If both these exist, then we say f is differentiable. Now, what is fx at a point a, b, c? Is nothing but we have to fix other two variables are constant. We have to differentiate with respect to x. Therefore, it's nothing but limit h goes to 0, f of a plus h, comma b, comma c minus f of a, b, c by h. If the limit exists, this is nothing but fx. So, what is fy? At a point C, A, B, C, you have to fix x and z are constant. You have to differentiate. Therefore, limit h goes to 0, f of a, comma b plus h, comma c minus f of a, b, c by h. If the limit exists, then that is f. So similarly, we can define all the derivatives: fx, fy, fxx, fxy, fxz, all possible derivatives. Okay. So this is a thing. Now, so we discuss about the continuity of all the thing. Now we discuss what is the maximum and the minimum of your function. Okay. So that is we have to discuss. So in the function of single variable, how we'll find the maximum or minimum of your function? First, you have to take the derivative. Okay. So maybe quickly we recall what we how we find the maximum and the minimum of your function in the single variable. Okay. Suppose f of x comma y is given in the single variable. We have to find the maximum and the minimum. What we got to do? First, you have to take the derivative of function and then consider this equation f dash of x equal to 0. And then from this, you have to solve x. You will get a solution x equal to something. Okay. Now, so this point is called saddle or critical point. Critical point. Now, what we have to do? You have to find the second derivative of your function. So, and then you have to substitute these values x. If it is negative, then the function get the maximum value at the point x. Then f has a maximum at a point x. So maybe if we take f dash of x naught is some solution. Okay. Suppose x naught is solution, you got to substitute in the second derivative. If it is negative, then f has a maximum at x naught. Suppose f double dash is positive, then it is minimum. F double dash of x naught is positive, then f has a minimum at a point x naught. So what is the minimum value? Is nothing but f of x naught is the minimum value. In that case, what is the maximum value? Is nothing but f of x naught is the maximum value, because maximum will get at the point x naught. So this is a function of single variable. Now, what is the maximum to minimum for a function of two variable? Okay, now we discuss that one. Suppose maybe we can extend this into an definition. Okay, so definition. Suppose f means, suppose I'm simply writing f of x. Suppose I take capital X equal to x1 comma x2. Maybe I can take any general case. Okay, I take n variable. So simply case, more we discuss about the general case. Suppose capital X I denote the n tuple x1, x2, etc. xn. So simply we can denote f of x. So what is actually f of x? Is nothing but f of x1, x2, etc. xn. Function of n variable is simply denote fx. Okay. Now, okay. So maybe, so what is the definition? As a local maximum. So when we say the function is local maximum, so local maximum means what? And at the neighborhood, every values is less than or equal to that f of x naught. Okay, so definition. So f has a local maximum. Local maximum at a point x naught. Okay, so again x naught is nothing but again some n tuple. Okay, x naught is some n tuple. So f has a local maximum at a point x naught if the value of f of x is less than or equal to f of x naught. So everything, every value of f is less than or equal to f of x naught comma f of x naught, then we say is a local maximum. Okay, for all x near to x naught. There is another definition, global maximum. Global means what? We have to look at the maximum for the entire interval. But local maximum at a point means what? You got to take some neighborhood of x naught and then look at what is the maximum of a function. So this is the first definition for local maximum. So similarly, we define local minimum. So that is f has a local minimum at a point x naught. If this f of x naught is smaller than all other value, f of x for all x near to this x naught. Okay, then we say f is local minimum at the point. So in the simple case, I can say we will discuss what is mean by local in the graph. Suppose this is a function, this is a domain. So the function is maybe, so this is a function f. Okay, this is a function f. Is defined on some interval. Now, suppose we want to find the local max. Suppose I fix some point x naught here. Suppose I fix some x naught. Now, what is the local maximum means? Suppose you consider some neighborhood of this interval. If you take any point x, so if you look at here, so this is the minimum value. If you find this is the maximum value. Okay, sorry. So in this interval, so we get some maximum, we get some minimum, right? So when we say this x naught is the local maximum, so the corresponding f of x naught is this one. Okay. So just I'm saying, okay, better instead of this one, I write the simple graph so that I can easily understand it. So the graph may be like this. Now this is a minimum value in this interval. Okay. But if you consider the entire thing, maybe this is a minimum value. This point is the minimum value. But if you consider this interval, at the point, minimum values may be this, maximum values may be this. But if you look at the entire thing, maximum value may be this. Okay, this is a global maximum, global minimum. Sorry, there are two different definitions, global and then local. Okay. Now, there is a theorem. Suppose a function either local maximum or local minimum at a point P, then all the partial derivatives are 0 at a point P. It's very important theorem. Okay. Suppose f is a function of n variable. So suppose if f of x1, x2, etc. xn is a function of n variable has a local maximum or local minimum at a point P. Local maximum or minimum or local, that is very important, local minimum or local maximum at some point P. Then the theorem says either the first thing, all the partial derivatives of f, that is dou f by dou x1, that is the partial derivatives of f with respect to x1, and this is equal to the dou f by dou x2, etc., dou f by dou xn. All the partial derivatives, first partial derivatives are 0 at a point P. Okay. Or either this is happen, or at least one of the partial derivatives does not exist. Or the second one is one or more of the partial derivatives what is the partial derivatives? Dou f by dou x1, dou f by dou x2. Among these n partial derivatives, either one or more partial derivatives does not exist at a point P. Does not exist at P. That is the theorem says. Okay. Suppose a function have a local maximum or local minimum at a point P, then all the partial derivatives are 0. Either all the partial derivatives are 0 at a point P, or one or more partial derivatives at a point P does not exist. Okay, good. So the next thing is what do you mean by critical point? So actually simply the del f, we can call a del f means what? Already we know what is the del f. Okay, so maybe I can write the notation del f. So del f means f of x1, x2, etc. xn is nothing but is a vector. So that is nothing but dou f by dou x1. That is the first coordinate. Second coordinate is dou f by dou x2, etc. Dou f by dou xn. This is del f. So simply saying, if suppose f is a local maximum or local minimum at a point, then the del f at a point P is 0. Or that is the first condition. Del f P is 0. So del f is nothing but is a n tuple. The first one is derivative of f with respect to x1. The second coordinate is derivative of f with respect to x2, and so on. Okay. Now, next definition. Critical point. We say a point is critical is del fp is 0. So for okay, so definition for critical point. When we say a point is critical, is del f is 0. So we say that a point P is a critical point. Critical point of f, of a function f, if you find the del f, that is dou f by dou x1, dou f by dou x2, all the functions at a point P is 0, such a point P is critical point. Okay, but not all the critical points are local maximum or local minimum. The converse need not be true. But if you suppose a function is local minimum, local maximum, the derivative is always 0 at the point P. Suppose the derivative is 0 for all points, then we cannot say the f has a local maximum and a local minimum. Okay, so the converse need not be true. So, but one way is always true. What is the one way always true? Suppose it's either local maximum or local minimum. Sometimes maybe, because here then either I am saying, okay, so either this del f is 0 or one or more partial derivatives does not exist. Okay, so therefore not all the critical points are local maximum or local minimum. Okay, keep in mind. Now maybe we can solve some problem to find the critical points. How to find a critical point? So this point also n-tuple, the critical point also n-tuple. Okay, this P is maybe some P1, P2, etc. Pn. Okay, so maybe we can solve some problem. Exercise. Find the critical points of the function. Though there may be the number of critical points may be more than one. Okay, keep in mind. So find the critical points. Point or points. If exists more than one, then points of the function. Of the function g of x comma y is x square plus 6 times xy plus 4y square plus 2x minus 4y. So there are two independent variable x and y. Now you have to find gx, gy. So derivative of partial derivative of g with respect to x. What is gx? Is nothing but 2x plus 6y because y is constant and then plus 2. So this is a gx. And what is gy? 6x plus 8y minus 4. Okay, so this is gx, gy. Now you have to take this is equal to 0 and this is equal to 0. We get a two equation, two unknowns. Therefore, the first equation we can cancel 2. Simply we can write x plus 3y equal to minus 1 from the first equation. From the second equation also we can cancel 2. So maybe we'll get 3x 4y equal to 2. Okay, now solve x and y. So what you can do? So maybe we can multiply, maybe you can call this equation number 1, this is equation number 2. Now multiply the first equation by 3. So what you'll get? Suppose I am going to eliminate x. Therefore, we get 3x plus 3 into 3, 9y equal to minus 3. So keep the second equation. So we get 3x plus 4y equal to 2. So just to subtract these. So 3x cancel. 9y minus 4y, we get 5y equal to minus 3 minus, this is minus 5. Therefore, y equal to minus 1. So substitute y equal to minus 1 either in the first equation or second equation. So therefore, if you look at the first equation, this implies so x minus 3, you can take that side, minus 1 plus 3. Therefore, x equal to 2. Therefore, the critical point is 2 comma 1. Sorry, 2 comma minus 1. So we get only one solution, right? So therefore, 2 comma minus 1 is the critical point. Critical point of the function g. Okay. Now we classify of critical points. Okay. So classification of critical points. So if you take n variable, you will get n equation and n unknowns, x1, x2, etc., xn, and then you can solve, you will get a solution. Sometimes you'll get a more than one critical point. Okay, so the next one is classification of critical point. Classification. Because when this maximum, when this will be minimum. Okay, so classification of critical points. Okay. Suppose we have some critical point. We call x naught comma y naught with a critical point of f of x comma y. So let the point P, that is x naught comma y naught, be a critical point. Critical point of the function f of x comma y. So that the first derivative of a function with respect to x at the point x naught comma y naught, because how will so critical point means what? Is satisfy the first derivative. We will find the solution using this. Okay. So therefore, if substitute this x naught y naught in the first derivatives of x and y, you will get 0, because that is a critical point. We know this. Okay. Now assume that f has continuous second order partial derivatives. Suppose assume that this f has a second partial derivatives exist. So and assume that f has second order partial derivatives exist. Assume f has continuous second order The second order exists and that should be continuous. Continuous second order derivatives. That is partial derivatives. Derivative exists near the point x naught comma y naught. Okay, assume this condition. Now we have some matrix H. So this matrix is called Hessian matrix. So this H is nothing but there are 2 by 2 matrix. So the first entry is fxx. This is fxy. That is partial derivatives, second derivatives. So these are all second derivatives. And this fxyx. But fyx is same as fxy because it's continuous. So and this fyy. So consider this matrix H. And we got to evaluate each of the term at a point x naught comma y naught. Okay, that is fxx of x naught comma y naught and fxy of x naught comma y naught, all the things. So we have to evaluate this H at a point. So evaluated at x naught comma y naught. Maybe we simply call some name capital X. So capital X is nothing but some x naught comma y naught. We have to evaluate each of the term of the matrix. Okay. Now, and this matrix is called, and it is called, and the matrix is called Hessian matrix. Called the Hessian of F at the point x naught comma y naught. Okay. Now, for example, maybe if you look at the previous example, so we know G. So what the Hessian of G? So already we know Hessian of G at a point some, I can take some point. Okay. Okay. So already we know Gx. So what is Gxx? Okay. So Gxx. Oh, maybe I can write here. So what is Gxx? Again, if you differentiate, we get 2. What is Gxy? You get 6. Again, what is Gyy? You get 8. Again, Gxy is also same. Now, what is the matrix H? Gxx, that is 2. Gxy, that is 6. Gyx also we get 6. And Gyy is 8. Now, here there is no x here. So, therefore, this is a Hessian matrix of a function G at any point because the matrix does not contain any variable xy. Okay. So this is a unique matrix for all points, but for it's not true for any function. Okay, maybe sometimes the matrix indices are some functions of x and y. So if you substitute the point x naught y naught, you will get that one. So therefore, that matrix is called Hessian of F at a point x naught y naught. Okay, now in order to determine the type of the critical point, we look at the matrix. So it's this matrix is very important. Okay. Now, what is the second derivative test? Now we list all the possible cases. Now, first, if the matrix H, right? So if you look at the determinant of the matrix H, so the determinant of the Hessian after substituting x naught y naught, all the entries of the matrix are constant. Therefore, we can find the determinant. It's a real number. Okay. So suppose the determinant is positive. Okay, at a point x naught comma y naught. The determinant is positive at a point x naught comma y naught, and the second derivative of f with respect to x, that is fxx at a point x naught comma y naught. So assume that x naught y naught is a critical point. Okay, suppose this is maximum. Sorry, that is positive. Then then this is a minimum occurs. The function have a minimum at the point x naught comma y naught. Then a minimum occurs at the point x naught comma y naught. If f double dash of f x of x naught comma y naught is positive and the determinant is positive, then minimum occur at the point x naught comma y naught. That's the first one. Suppose the determinant is positive. If the determinant of the SCN is positive at a point x naught comma y naught, but this fxx is negative. Fxx of the point x naught comma y naught is negative, then a maximum occur. If negative, then maximum occur at a point. Maximum occurs at x naught comma y naught. Now, third one is, suppose the determinant is negative. Suppose if the determinant of the ACN is negative, then we say the point is saddle point. Then a saddle point occurs. So saddle point occurs at the point x naught comma y naught. Okay. Now, suppose the determinant is 0. So the next one is, suppose if the determinant of H is 0, then the test is inconclusive. That is, and the nature of so we cannot say the nature of the critical point x naught y naught. Okay, so then the test is inclusive. The test is inconclusive. We cannot conclude anything. Conclusive. And the nature of the critical point, nature of critical point x naught comma y naught cannot be determined from the second derivatives. Cannot be determined from the second derivative. Second derivatives. Okay. So that is the thing. So maybe we will discuss some example. Maybe we will suppose that for the determinant equal to 0 case, we will discuss later. Now maybe we discuss some example. Suppose find the and classify the critical points. Okay. Find and classify the critical points of the function f of x comma y equal to x square y minus x square minus 1 by 3 y cube. So first we have to find the critical point. So how we will find the critical point? You have to take the first derivative and then take equal to 0. So what is fx? So fx is nothing but 2xy minus 2x. Okay, because this is 0. What is fy? Is x square, and this is actually 3 cancel, we get y square. Got it? So from this, therefore, if you consider xy equal to 0, we can get, we can cancel 2. We get x into y minus 1 equal to 0 from the first equation. Suppose if you consider fy equal to 0, we get x square minus y square equal to 0. That is x plus y into x minus y equal to 0. Okay, otherwise simply say x square equal to y square. Okay, x square equal to y square. Now what are the possible? So since here product is 0, x into y minus 1 is 0. So either x equal to 0 or y equal to 1. Okay. But now if we look at the case, therefore there are therefore for x equal to 0, if x equal to 0, from this y should be 0. Because if x equal to 0, then x square equal to y square, therefore y square should be 0, therefore y is 0. Okay. So for x equal to 0 implies y should be 0. Okay. Suppose for x equal, for y equal to 1. That is because when this product is 0, either x equal to 0 or y equal to 1. If x equal to 0, then y should be 0. If y equal to 1, now substitute y equal to 1 from this, therefore x square equal to 1, therefore x should be plus or minus 1. Okay, therefore x should be plus or minus 1. Therefore, what are the possible critical points? For the first case, 0, 0 is one critical point. And if you fix the second, y is 0, then either 1 or minus 1. So there are three critical points. 0, 0, 1, 0, minus 1, 0. So there are three critical points. Now we have to classify the nature of this one. So first we need a second derivative. Okay, fxx, because for the Hessian matrix we need a f second derivative, right? So what is fxx? So fxx, already we know fx. So again, if you differentiate with respect to x, we get 2y minus 2. And what is fxy, yy? So yy is nothing but just minus 2y. And what is fxy? You get 0. Even if you find yx also 0. Okay. Now the Hessian of h equal to fxx. Fxx value is nothing but 2y minus 2. Fxy value is 0. And fyx also 0. And this fyy, that is minus 2y. This is Hessian matrix. Now at each point, we have to look at what is h. So there are three critical points. First at 0, 0. So at 0, 0, if substitute x equal to 0, y equal to 0 in the h, what is the determinant of h? So it's nothing but determinant of, if substitute 0, we get minus 2, 0, 0, 0. It's nothing but determinant 0. Okay. Therefore, the test is inconclusive. Therefore, the test is inconclusive. Suppose at the point 1, 0. What is the next critical point? 1, 0. So substitute x equal to 1, y equal to 0, but in the determinant and the matrix, there is no x term. Okay, therefore substitute y, we get minus 2, 0, 0, 0. Okay, so therefore we get determinant 0. Sorry, I think I did some mistake. Okay, sorry. So nobody is mentioning me. So if for y equal to 1, right? So therefore the second quad is 1, not equal to 0. Actually 1. Y is 1. Sorry. So therefore the critical point is 1, 1. At a point 1, 1. So if substitute y equal to 1. So if y equal to 1, this term is 0. Correct? And this term is 0, 0. And this is a minus 2. Correct? Therefore, what is the determinant? Oh, sorry. Again, this also minus 2. So again, okay, what is fxy? I am writing right. What is fxy? No, I think so. Please wait. We will check the matrix again. So fxx, okay, 2y minus 2. Fyy is nothing but minus 2y, correct? What is, okay, sorry, fxy is, I am going to differentiate these with respect to y. Okay, so sorry, fxy. Therefore, we get 2x. Suppose if we differentiate with respect to y, we get this. And what is fyx? we get 2x. Yeah, 2x. So in the corner we have a 2x, right? Sorry. So this is actually 2x. So I am correct. It's 2x or 2y. 2y only, I think, because if you take x, okay, yeah, correct. Minus why? So fx is correct. So if you differentiate y, then you get 2x, right? Fxy.
Yes.
It's not minus 2x or minus, yeah, it's 2x only. So now, anyway, this is okay, correct. First case is okay. Now the second case, if substitute y equal to 1, x equal to 1, in that case, we get, if substitute y equal to 1, we get 0 here. This is 2, and this is 2, and this is minus 2. So anyway, the determinant is minus 4. Okay, so the determinant is minus 4 is negative. And we know that, okay, now we so from the classification, if determinant is negative, look at this one, it's always saddle point. Okay, therefore this 1 comma 1 is a saddle point. Then the critical point 1 comma 1 is a saddle point. So the last critical point is minus 1 comma 1. Now what is the determinant of the ACN? If substitute x equal to minus 2, sorry, minus 1, y equal to 1. If substitute again y equal to 1, the first entry is 0. So this is 0, and this is a minus 2, this is also minus 2, and this is also minus 2. The determinant is now 4. Now it's positive. Now if x is positive, now what is fxx? Because we want to find that fxx also positive or negative. So what is fxx? So fxx is nothing but 2y minus 2, right? This is the first point. Fxx is nothing but 2y minus 2. At a point 1 minus 1 comma 1, what is the value? Is positive or not? So substitute at a point minus 1 comma 1 at this point, x equal to minus 1, you will not get anything. But if substitute y equal to 1, you get 0. At a point, this point, this is, sorry. The determinant also minus 4, right? Because 2 in minus plus, and then formula have minus. Sorry. Therefore, is minus 4. Then the point minus 1 comma 1 also saddle point. So therefore, we cannot find the maximum minimum of this one. Okay. Anyway, we can stop now. We'll discuss more problem in the next class. Thank you.